Is it possible to make a mechanism that transforms between a cube and an octahedron? This is the challenge that this guy, Robin Jamais, nerd-sniped me with a couple of months ago. All right, so I'm here with Robin Jamais. So yeah, where are we? What are we doing?
Okay, we are in the Étincelle du Palais de la Découverte. It's a temporary place where we have public and students are coming to hear about
Science and mathematics.
And mathematics,
yep.
Because my job is explaining about mathematics to everybody, from 6 to adult.
Perfect.
Yes, the Palais de la Découverte is a museum, a science center, but it's in work.
Or remodeling. So this is the temporary, but very beautiful space where, and we're in Paris.
Yeah.
You nerd-sniped me with a problem.
Yeah.
So what is the problem that?
So to begin, I think a lot of people know this, but we have to explain this for everybody. These two polyhedra are different, but are very related because you can see in different ways. For example, each time that you turn one in the manner that it's the same position at the end, the other can do the same. So
the cube and the octahedron
have the same symmetries.
Have the same symmetries, yeah, exactly. And if you can kind of line them up, right? For every corner, every vertex of the octahedron, you've got a face of the cube. So 6 vertices and 6 faces, and the other way around as well. For every corner of the cube, there are 8 corners, there are 8 triangles.
Yeah, that's a way of seeing the duality, is to say you take vertices on each face on the cube, and then you will have the vertices of this one. So
we have a much better, here we go. Yeah.
I had to explain this before, but we can see it very well there. On each face you have vertices, and then you have this one. And if you take a vertices on each face of this one, you come back with the cube.
Yeah. I guess if we line it up like this.
Yeah. Sorry.
Then, yeah.
And then you can see it when you make the cube bigger. You can make that the edges are cut at the middle, and so.
Oh yeah. So if you sort of try and make them the same.
So they are the same size. We can say it's not the same size, but if you do the same size, you can see both together, and then you see that it's just 90 degrees, a quarter of turn.
When you go from the edge of the octahedron to the edge of the cube. Yeah.
Yeah. And then I had the idea that we could pass from the cube to the octahedron
just by
turning this.
Right.
Okay? And my first idea was, there are 12 edges. When we are 6 persons, we can have tried to make a cube with little things like, I don't know, things like this.
Right.
And then, we are not enough. We are only 2, but
you want to do this, this kind of...
Okay, and then when you turn in the right way,
somehow you will make the
from
things.
the cube to the octahedron. It's not so easy if people want to do this.
And you tried this out with...
Yeah, I tried it. With normal people, it was very difficult. And then with mathematicians, it was not so easy.
It's still kind of difficult.
It's still, yeah. Allez, 1, 2, 3. Yeah. 1, 2, 3. And we had one of the first attempts. The first was with little things like this, and then we wanted to be to do it bigger, and we found just the first thing that we found at the moment. It was in Switzerland. It was in an hotel, and we found a club, the
golf club.
Club.
Mini golf.
Mini golf. Yes, mini golf. Mini golf.
I mean, you could.
Yeah, we could. And so yes.
And it kind of worked. Okay.
And it worked. We have the video. It worked well. And then I thought, okay, it's not so easy for normal people, and we have to be 6 and to see the cube.
You need a lot of people.
And wouldn't it be possible to find a mechanism that
just do it.
To do it.
Yeah.
So an important issue to make a mechanism.
To make a mechanism that does.
Well, okay, it's difficult because you have 12 12 sticks and you want them to move together.
Right.
And another problem is that this length is not the same as this one.
If you just rotate like this around the midpoint of the edge, then they're different lengths. Yeah, right. So it's not the same stick.
And you can see it when you do the experiment, because you have to do
with the
closer. Yes, with
golf clubs
with people,
or whatever.
You have to be closer. Or
Right.
So it's a problem more than 12 together.
More than just rotating.
Two big problems.
Right. The version of this question that I heard was really just, can you turn a cube into an octahedron? So this is 2 copies of the first answer to this. I was actually thinking about, like, maybe you could have the actual faces as well that somehow reconfigure to make the other one, which would be cool. But anyway, but then I realized, yeah, this is too hard. So let's just do the edges. This was my first idea, have the edges rotate 90 degrees and also somehow move inwards and outwards, perhaps using a screw mechanism. But I was worried about how much friction you'd get with that design. My next thought was to have 2 sticks per edge rotating in opposite directions. Then the ends of the sticks can meet up with each other and we could put a joint there. This is very similar to the jitterbug mechanism. Here's a geared version of that I made with Sabeta Matsumoto. Here there are Y-shaped parts that hinge onto each other at their endpoints, and they rotate around as the structure expands and contracts. So the same kind of thing might work here. I got as far as making this animation before discovering that I had been scooped by a paper published only 3 months before, reconfigurable polyhedral mechanisms using scissor-like elements with cantillation transformations between dual geometries by Yuan Liao, Gokhan Kuiper, and Sudarshan Krishnan. It has exactly this mechanism in it, as well as lots of other interesting polyhedral transformations. But I still wanted to make a copy to see how it works. So this will do the transformation from the cube to the octahedron and back again. And I guess the point is that making it a linkage with these hinges means that it figures out the distances, right? They actually get further away than both the cube or the octahedron when you're in the middle point. What is
this one on the middle?
Oh, what is the shape?
Yeah,
what is this thing? Good question.
What is this thing?
Yeah, so in the middle, you have these like flat
kind of
hexagons.
yeah.
There's 4. Let's see, can we see the hexagons? 1, 2, 3, and then the 4th one is here. So those are 4 hexagons corresponding to the 4 long diagonals through a cube. And it's sort of bendy, but you can sort of see, like, there's like a square here and a triangle here. So these are squares and triangles. So that's a cube-octahedron,
yeah.
which is pleasing somehow. It's halfway between a cube and an octahedron.
It's this one, but you cut all. If you take this one and you cut.
Oh, yeah. If you chop all the pyramids, cut all of those off, and then you get this. So this kind of works, but it does other things. So I'm being very careful to do it the right way. And it helps that I'm on the table.
It's not so easy.
It's not so easy. So here's the problem.
First time I try it.
Yeah. So there's all of these hexagons, these zigzag hexagons, and they all have to sort of zigzag the correct way at the same time. So if they all zigzag this way, then you get the octahedron. If they all zigzag the opposite way, see, it's already doing it now. You get the cube. But if one of them is out, if one of them is off, oh, that's 2. Oh my gosh. Like this, it's not quite a cube. It's certainly not an octahedron, because this hexagon is not flipped the right way. And then, like, if 2 of them go if you get 2 and 2, then you get this thing, which is neither a cube nor an octahedron. And, like, let's see, can I get the 3rd thing that it does, which is not what I want? Yeah. You can also get this, which is not quite an octahedron. So I don't know.
It's not so easy.
It's not so easy. It becomes more of a puzzle than it just immediately does the thing, which is also interesting. Like, sometimes it's good to have, like, that sometimes it's good that it doesn't just automatically do the thing, but you have to work for it and it becomes a puzzle. Okay, But let's see the second version. So let's get rid of these ones.
And
All right.
I don't know it.
The reveal. So this is the new version in the cube form, and then yeah, you turn the edges.
Okay.
Okay. Well, let's find out. Is it easy to figure out?
Pop, 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 pop. Wow.
Ta-da!
So beautiful.
Here's the animation showing how this mechanism works. There is a core with 18 bevel gears. This is similar to designs like the gear cube. The gears make sure that all of the edges turn the same way at the same time.
So my idea was that the mechanism would be something with a
With a screw.
a screw
Yeah.
to be not
To come in and out.
to come in and out. And this, but this is okay.
This is a different way to do it.
But it's very okay. It's
These two are very much the same geometry. And we said before, look, the problem is that this edge is not the same length as this edge.
yeah.
So you can solve it either by moving things in and out or by changing the length of the edges.
And it's okay.
So
it's a very good
seemed easier.
solution. Yeah, and then the gears inside.
Yeah, you can actually go a little bit further. Yeah, yeah, so that it kind of clicks in past. There's a little bit of it actually cheats when you're going in towards the cube. That like the mathematically perfect thing, they actually pass through each other just a little bit.
Yeah.
This is a very rare case we should appreciate when the real world is actually better than the mathematical ideal. Most of the time it's not like that at all, but here it's like, yeah, it'll go past and it'll click and yeah.
And then the black gears that the faces of the cube and the vertices of the octahedron.
Yeah, the black gears are the vertices of the octahedron, and the white gears are the edges of the octahedron. So you could ask, where are the vertices of the cube? Why aren't there gears for the vertices of the cube?
Because you have only 6, so it's better.
6 is better than 8.
Than
exactly.
8.
Yeah. So
okay.
It was going to be one or the other, and with 6 is just fewer parts, and also it means that the length of the loops of gears is shorter. These are loops of length 6, and if you put gears for the corners of the cube, you would have loops of length 8, which is just a little longer. Anyway, yeah.
Okay. Yeah, it's
so,
okay.
Okay, maybe this answers the question.
I don't have anything that it says, and thank you. It's so beautiful. It's so incredible.
There's one other thing. These gears in the middle, they don't turn.
Yeah.
Because they're attached to the core in here. So they don't actually, it's really weird to see that the gears don't turn.
They don't turn.
The orange gear in the middle, it doesn't move, which looks very strange that the edge moves around it, but the gear isn't actually moving. The racks are turning. After I visited Robin, Sabeta Matsumoto and I modified the first design to fill in the faces of the cube and the octahedron with fabric. In the cube state, there are 6 blue squares of fabric. As we transition to the octahedron state, those blue squares fold away into the vertices, and 8 orange triangles expand to fill the faces of the octahedron. We added tethers to the centers of the faces that meet in the middle. These make sure that each face folds up inside and doesn't flop outwards. We also modified the 3D printed connectors by adding holes for thread to go through to attach the corners of the squares and the triangles to. The visual change is pretty striking now. It's always fun when you can get something to change color, particularly if you can get it to change color quickly. These fabric patches don't help much with getting the mechanism to only go between the cube and the octahedron. It's still pretty easy to get it to go into the other states. So this is the almost cube, except it looks pretty interesting now with the alternating blue and orange patches. Let's see if I can get the other 2 strange things to happen. Yeah, this is the one that's halfway in between, sort of neither cube nor octahedron. And if I flip one more like this, then we get the almost octahedron. And again, I think they look pretty cool. It's got a sort of circus tent vibe to it with the alternating bright colors. So some further challenges. Is it possible to make a mechanism with a geared core but where the edges do in fact move towards and away from the center rather than changing length? And if so, can it be done so that the gear is rigidly attached to the edge, or would you have to have separate parts for the rotating gear and the edge itself? And the dodecahedron and the icosahedron are also duals, so what about making a geared transforming mechanism for them too? As usual, I'll put a link to the files for both of these designs in the description. And I've put an extra something from Robin Jamais at the end of the video, but first, many thanks to the Étincelles du Palais de la Découverte, apologies for my French pronunciation, to the Institut Henri Poincaré, which I've been visiting here in Paris, to Maison Poincaré, and to the Fab Lab at Sorbonne University, where I did the 3D printing and laser cutting. And also, of course, thank you to my Patreon supporters. Okay, here's Robin telling us about a model of the Borromean rings. This is showing what this place is about.
I don't know if you showed, I showed you this last time, but probably what? Yes.
The Borromean rings?
Yeah, the Borromean rings. And we wanted one in our cabinet curiosité, so yeah, we have the big one there. Big one.
Oh, okay, yeah.
Very big one. And, but we wanted a little one too to show to people because it's heavy. And I asked it for a colleague, an engineer, and I told him, okay, you cut a ring, and so we can make them together. And he haven't.
Oh yeah. How does it come apart?
He haven't cut the one that I've seen before I asked to him. The three was cut with a magnet. So it was easy
together. Yeah.
And he did it for me with just one open just once.
Ah, I see. Okay.
And it was totally not clear for me if it's possible or not to do this now.
Oh, to put it together. Yeah.
Because it's not so. It's not obvious that it will be.
Right.
You know.
Right.
And it was an involuntary puzzle. Exactly how you say.
An involuntary
puzzle.
Oh, that doesn't translate to English amazingly well. So
no.
What do you like was maybe a natural puzzle?
Yeah.
It just came out of trying to make the thing.
Okay, he didn't want to make a puzzle. I didn't want to make a puzzle, but it
just happened. Yeah.
And I wasn't not sure that it was possible. You know, so the first time I tried, probably I needed 15 minutes or something like this.
Oh, to put it together.
Because it was not.
It's not obvious. Yeah.
It was. Yeah, it's not obvious, and it was very. It was out of the machine, and so it was not so easy to.
Yeah.
I didn't want to break it, so I was very careful, and so I found a way to think about this and to find a solution, because it's cut there. And not there.
Oh, and that makes a difference.
Yeah, because at the end, you know that, for example, this one, it will be outside the red one and inside the green. And so to finish, to do the Borromean rings, you need to, once they are linked, and then they don't, they are not linked
then you need to
again,
unlink
because
again.
you need to unlink. And you know that the last movement that you can do is from this part.
Right.
So
right.
Let's say you know that it will be to go in a ring and not out a ring. To go out a ring, you need the big axe and not the little one.
Okay.
So you know that you have to go in the green because you will end in the green and
Oh, so then you turn it.
And then you turn it and go in.
Oh, wow. Okay.
And with this way of thinking, it's okay. You find a solution. But it's not so easy.
It's not so easy. Right. I mean, topologically, I'm like, yeah, sure. The Borromean rings, they're not actually, they're not pairwise linked. So you should be able to do this. But it's interesting that you have to sort of
Yeah.
You have to link and then unlink to.
And so
to-
if
to
you
put it
if you
together.
if you cut there and not here,
Right. Then you think
the
it won't
movement
work?
will be totally different.
Oh, have you tried it?
No.
With the cut in the other place?
No, but I have to because it's that means you have to come in the red one
Right.
and then and then out.
Right.
Okay,
Right, right.
from this place. So probably it's the same,
Probably you can do it, but
but it's not so clear.
it's not so obvious.
Yeah, it's not so obvious.
Cool. Awesome.